Alright everyone, welcome to module 5.3. In this module we'll be extending the method of virtual work to frames, which will be essentially combining virtual work for trusses and virtual work for beams into one equation, which means we will be considering work done by axial forces, like in the case of trusses, as well as work done by moments, as in the case of beams. So we'll first establish the general principle for virtual work for 2D frames, and then we'll compare deflections resulting from bending and axial effects to get a sense of how much each of these contribute to overall deflections. So the first thing we need to do is establish an equation for the virtual work done by an axial force. We already did this in module 5.1 when talking about trusses. However, now we need to consider that beams may have non-constant axial forces. So in general, an axially loaded beam will look like this, where it has some sort of distributed axial force. So if I take any segment of this beam, dx, then the internal force in that segment will be a function of its position. So the internal axial force in this segment I'm calling f of x, and I'm going to assume that for any small segment that's going to be constant. And that's going to cause the segment to deform by a value d delta. So in a very similar fashion that we established the infinitesimal work for moments, we can establish it for axial forces as well. And using the relationship between internal forces and deformations, we can simplify this all in terms of x. So the total work done by the axial force in a beam is going to be the integration of the infinitesimal work over the length of the beam. And of course, when we talk about virtual work, the force applied to the beam will actually be the virtual force. So the virtual work equation will look a little bit different, where one of those forces changes to the virtual force. Now notice that in the case when the internal forces as well as the properties of the beam, E and A, are all constant, the equation simplifies to the following. And if you've been paying attention, you'll notice that that is exactly the same as the equation for virtual work, internal virtual work in a truss. So a beam is just a more general representation of a truss element. So plugging this term in to the equation for virtual work that we established before, we simply get an expanded version. So on the right-hand side, representing the internal work, we have the work done by the moment or from bending. Then we have our work done by the axial forces. And then on the left-hand side, for the external work, we have our usual PV times delta value, as well as I've added the work done by support settlements, which doesn't change from the expression we used in the truss case. So this is the most general equation you can have for virtual work. And to iterate the point from the previous slide, if we introduce a couple of simplifications, we can actually just get directly to the equation for virtual work for trusses. So in this case, of course, we have to sum over multiple truss members. So that's all we really need, and we can start on an example. So take the following frame that is being loaded downward by a distributed force and laterally by a point load at point D. We're being asked to find the deflection of that point D using principle of virtual work, and we have constant values for E and I for the entire frame. So the step-by-step process is the same as the one we established with beams. So the first thing we'll do is draw the real and virtual diagrams, as well as the deflected shapes for the real diagram. These have been conveniently drawn for us, so I'll simply label them, and now we can draw a guess of what we think the deflected shape might be. It doesn't have to be exact. It will look something like this. And so we're looking for the deflection delta D. So we need to draw a virtual load on the virtual system in the same direction at D. So the next thing we'll need are the reactions for both the systems, as we'll need them when solving for the internal moments and axial forces. And now we're ready to move into step 2, which essentially consists of breaking this into little chunks that we can solve. So as we usually do, we'll split this into beams first, so a beam AB and a beam BC. And then we'll also need to split it into sections of continuous loading. So first we split it into 2 beams, and then we notice that we'll need 3 sections here. A section 1 before the point load, a section 2 after the point load on AB, and then just one for beam BC, which we'll call section 3. Then we need to set the constants of integration, being careful to be explicit of which is which. So I'll set my constant of integration for beam AB to be 1 for the whole beam. I could do 2 different ones for both sections, but just to keep it simple, I'll set it to 1, and I'll call that x1, and that'll start from 0 at A. And I'll use x2 for beam BC. Okay, so let's start with section 1. My constant of integration is x1 here. And now we're interested in both internal moments and axial forces, so I need to solve for both of those. And I'll use my positive conventions here, m counterclockwise and n1 in tension. So solving for both of those, I get the following results. So n1 equal to negative 6.3 kips. That means that section of the beam is in compression, and m1 is a positive 40 times x1. All right, moving on to section 2. Same procedure here. I'll solve for moment m2 and a axial force n2. And sum of forces in the y give me n2 equal to negative 6.3. So same result as section 1. The beam is simply in constant compression. And then sum of moments around the section point O actually give me a constant moment of 480 kip feet. And finally section 3, and actually here I will change my mind and change my constant of integration so I don't have to solve for the internal forces at B. So I'll change my constant of integration x2 to be from C. Therefore I have this free body diagram, and again I'm interested in moments and axial forces. So my final results are sum of forces in the x direction give me no axial forces in this beam, and sum of moments give me the following result. Notice how I accidentally used the negative convention for moment 3. I should have drawn that the opposite way, but because we're dealing with work, the signs actually won't matter as long as we're consistent. Now we can move on to the virtual system. So let's again start with beam AB, and let's add the reactions. And we'll also add the virtual force at D. So this beam we should split into two sections, just as we did with the real system. And I'll use the same constant of integration here. So again, we'll go ahead and solve for section 1. There's my free body diagrams. From sum of forces in the y direction, I get N1V equal to 0.4 kips. And from sum of moments around 0.0, being mindful of my constant of integration, I get M1V equal to x1. For section 2, here's my free body diagram. And the solution to the internal moments and axial forces are 0.4 in tension for the axial force and 12 kip feet for the moment. And finally, we have section 3 in beam BC. Draw the reaction at C, which is 0.4 kips. And I'll use the same constant of integration. I'm forced to, of course. I should have the same constant for both the virtual system and the real system. So in this case, I am bound by whatever choices I made in the real system. And in the same way, I'm bound by the same choices I make when choosing the convention for the axial forces and moments. So the only thing I need to make sure of is that I choose the same directions for both. So because I chose a negative moment convention here, I'll go ahead and do the same here. That's really what's important. So solving for the sum of forces in the y, we get the axial force to be 0. And solving for moments, we get M3V equal to negative 0.4 times x2 kip feet. Now I have all the internal forces and moments that I need. So I just set up my principle of virtual work equation. On the left-hand side, I just have the external virtual work done by my virtual force. There's no support settlements, so everything else is 0. And then I have this integral over the entire frame for both bending virtual work and axial virtual work. Now, I chose to use N for my axial forces, so I should update this equation. You're free to use whatever variable you choose. So let's start by considering first just a deflection due to bending. So we'll denote this as delta D bending. And that's going to be equal to this term integrated over the 3 sections separately. So we have the integral over section 1. It's going to be mv1 times m1 over ei dx plus the integral over section 2, which is mv2 times m2 over ei. This should be x1, right? And then this is also x1. And then finally, the integral over section 3, which would be mv3 times m3 over ei times dx2. And so breaking that out, we can take the ei to the outside. That's constant for all terms. And then we have the integral from 0 to 12 of x1 times 40 times x1 integrated over dx1 plus integral from 12 to 24 of 12 times 480 dx1 plus the integral from 0 to 30 4.04 x2, so that would be negative times negative times 1.5 x2 squared over 2 plus 38.5 times. Notice that if we had used a different convention for section 3, the signs for those two terms would simply flip and we'd get the same result. So evaluating those integrals, we would get the following. And then evaluating each of those terms and summing everything, we would get 169,000 roughly. Notice that the units are in kip squared times feet cubed, right? Because we have two moments being multiplied times a length. Everything was in feet. And so we need to, in order to match the units that were given for E and I, we need to multiply by 12 cubed to convert that quantity to inches. Then we simply divide by the terms for E and I, and our final result is 4.03 kip inches, which we then simply divide by that unit virtual force to get our final deformation due to bending. So our final answer is delta due just to bending is 4.03 inches. Now we can do the same for the work due to the axial deformations. So now we will consider only this term. And because we didn't specify a cross-sectional area, we'll just take that to be 13 inches squared. So the process is exactly the same. We start by calculating the integral over each of the three sections separately. So our equation looks like this. We know that NV3 was 0, so we can simplify this by just ignoring the section 3 integral. And so continuing that, we expand the integrals. In this case, both integrals are the same, so in fact we can consider it as one entire integral. And so in the end we get something pretty simple, which is negative 2.6 times x1 from 0 to 24. Evaluating that and plugging numbers in, we get the following. Notice now that the terms in the integration are in units of kip squared times feet, because we had a product of forces integrated over length. So in order to get into inches, we simply multiply by 12, and then we divide by our EA value, and we get negative 0.02 kip inches, which when dividing by the virtual force gives us a displacement due to axial deformations of negative 0.02 inches. Okay, notice that this displacement is still lateral. We're not talking about vertical displacements here. Okay, so our total displacement is the displacement due to bending plus the displacement due to the axial deformations. So in this case, 4.03 minus 0.2 inches. So notice, obviously, that the displacements due to bending are much, much larger, 2 orders of magnitude larger than the displacements due to axial deformations. So in a lot of cases, it's also acceptable to simply ignore axial deformations. In fact, some examples will specifically ask you to ignore axial and consider only bending. So important to keep those relative magnitudes in mind. So in summary, we've established that principle of virtual work can be used to compute displacement in frames by considering both axial and bending deformations, but essentially using the same rules as beams. We've shown that bending stresses usually result in the largest displacements for most common types of frames, and we'll generally ignore shear stresses and deformation due to those stresses as long as we're dealing with slender beams. And in fact, we can usually ignore axial deformations as well. Just be clear about your assumptions when solving these problems.